Good evening, students. Today I will continue my lecture from the graphical representation of the SHM. In the previous lecture, I have already discussed what is SHM and what is the differential form of SHM and the corresponding from the differential form, how the normal form of SHM can be derived. Okay. So, today we can discuss the differential form of SHM as well as next the original energy for the SHM. Okay. So, let us continue. So, in general, an SHM, what is the definition or what is the general form of SHM? That is y equals to a sin omega t, right. Instead of this omega, we can write a sin 2 pi t by capital T, right. Now, what will be the v corresponding this? V will be, that is basically dy dt, and if we do the differentiation, then what will be the value? That will be a cos omega t, and instead of this we can write a omega, here will be a omega cos omega t, that will be sin 2 pi t by t plus t by 2. So, this is the velocity part, and what will be the acceleration? Acceleration is the derivative of the velocity, that will be basically a equals to minus a omega square sin omega t. So, a omega square sin of 2 pi t by capital T plus pi. So, this is the calculation of acceleration, velocity and the displacement of a SHM. Okay. So, therefore, from there what we can conclude? We can conclude that how this time period or the time will change, that is this may be t by 4. If we consider graphically, suppose this is the representation of SHM. So, here if it is basically the graph of y, it is representing y. Okay. So, what is this point? This is 0, this is basically t by 4, this is t by 2. Next again this will be basically, this will be t, this will be 3t by 4, like this the graph will move on. So, this is the graphical representation of our graph of the displacement. If I want to draw the graph of velocity, what it will be? It will be basically like this. So, this is the graph or curve for velocity, and for acceleration what will be the curve? The curve will be basically, will start from this part. Like this it will go on. Okay. So, this is the curve of acceleration. So, in this way we can represent the velocity, displacement and acceleration of the SHM. Now, total energy of a particle in SHM. A particle executing SHM possesses both potential and kinetic energy. It possesses potential energy on account of its displacement from the equilibrium position and kinetic energy on account of its velocity. So, thus this energy varies during oscillatory motion, but their sum remain constant if no dissipative force are present. Okay. So, let m be the mass of the particle in SHM and y be the displacement from the equilibrium position at any instant. If a be the acceleration of the particle at that instant, then by the characteristics of SHM we can say A equals to minus omega square y, where omega square is the constant and the magnitude of the restoring force acting on the particle at this instant is given by, suppose F equals to basically mass into acceleration, that will basically m omega square y. Okay. Now, if the particle undergoes a further infinitely small displacement dy, then the work done against the force dw is basically the, this is, so it will be basically m omega square y dy. Okay. Now, the total work done, so what is the work done? That leads us to the energy, right? So, the total work done for displacing the particle through y can be obtained by integrating the RHS of the equation. Okay. So, if we integrate this, so m omega square is the constant, d omega. So, let us discuss this integration part. So, we have that integration of d omega. So, the limit is 0 to w. Zero to y, dy. M omega square is the constant, 0 to y, y of dy, and here will be omega, sorry, this is not omega, this is w. So, it becomes half m omega square y square. So, this is the work done, okay, and whatever the work done, that is nothing but the energy. So, this is basically, this W is defining the potential energy U. Okay. Now, coming to the kinetic energy. For the kinetic energy, V is required, and V is nothing but omega into A square minus Y square. So, K equals to half mv square. So, it becomes half m omega of A square minus Y square. Now, potential energy U is defined as half m omega square Y square. So, if you add these two, potential and kinetic, so total energy becomes basically half m omega square x a square. These two terms will cancel out with each other. It is evident from the equation that the total energy of the particle is free from the displacement y, that is, basically it remains same during the motion of the body. In the position of maximum displacement, that is y equals to a, the total energy is in the form of potential energy, while in the equilibrium position, when y equals to 0 basically, then the total energy is the form of kinetic energy. So, basically when a body is moving, when it comes to this position, here that is maximum displacement y equals to a, then the total energy is basically u is there, potential kinetic energy is 0, and when it comes to here, potential energy is 0, kinetic energy is there. So, by this thing, potential converts into kinetic, kinetic converts into potential. Okay. Now, already we know that total energy for the SHM E, that is equals to half m s square omega square. Now, if we want to represent this omega in terms of frequency, so it becomes basically, instead of omega, if we put 2 pi I, omega equals to 2 pi n, n is the frequency, then it becomes basically 2 pi square m n square s square. So, this is the generalized term for the energy in SHM. Okay. So, what is the graphical representation for this energy? So, basically the graphical representation is like this. This is 0, kinetic potential energy. This is 1, that is basically potential energy, and this is basically the kinetic energy. It is minus a, it is plus a, it is minus a. So, this is the representation, graphical representation of the energy for the SHM. Okay, hopefully it is clear. In the next part of the syllabus of the video, you will get the functionalities of the simple pendulum, and later on the restoring force as well as the horizontal oscillation of the mass attached to the spring. All these things I will discuss. So, thank you.